So we're going to get some practice with trigonometric substitution. Remember, you use the Trig Sub technique whenever you see something that looks like Pythagorean theorem. So the sum or difference of squares. And actually, in my opinion, this technique isn't too bad. I think it's a lot easier than U sub or integration by parts or trig integrals, because you don't really have to worry too much about, oh, what do I make my u, what do I make my dv, which identity to use really. You just follow this table based on what you see. Depending on what sort of Pythagorean theorem situation you see, you'll use one of these three table entries to make your substitution. This is trig substitution, so you're trying to get x's out and thetas in. A lot of times you will find yourself using these trig identities, so make sure you have those memorized. Sine squared plus cosine squared is equal to 1, and all the rest of them. And of course, you don't want to forget to draw that right triangle right after you make your table substitution. And if you don't know what that means, you'll see in a second. So we'll get started with this one. So I look at my problem. I definitely see the sum or difference of squares, so I know trig sub is the technique to use. And it looks like this is the table entry I'm going to use, because I have a number squared minus something with x in it getting squared. So I know a squared is 1, so I take the square root. A is 1. And I know f squared is this 4x squared, so I take the square root, and I discover that f is just 2x. So I got a, I got f. Looks like I'm all set up to make that table substitution. I will get this. Right before you do anything else, you want to make sure you draw the right triangle that this sine of theta situation describes. And the best way to do that is to get sine of theta by itself. So I do that. And I know sine of some angle is just the opposite, which is 2x over the hypotenuse, which is 1. So if I do that, I'll end up with this right triangle. My opposite is 2x. Here's my opposite. My hypotenuse is 1. Of course, I want to figure out what this adjacent is. Well, I can do Pythagorean theorem on that, no problem, to get this. So my adjacent is just the radical of 1 minus 4x squared. Okay, so now that I have my right triangle completed, just remember, always do that as soon as you make your table substitution. But now that we're done with that, this is very much like a u sub, but our u, in a sense, has already been chosen for us. I just want to get all of our x's out now and thetas in. So I get x by itself here, because I know I want to make some equation in terms of theta to plug in for x here. And of course I want to also get my dx out of here and put something in terms of theta in. So I have to take the derivative of this equation right here. That gets me cosine of theta over 2. Of course I want to multiply this equation on both sides by d theta, so it essentially moves over here. So I can get my dx by itself, which I know I want because I want to get this dx out of here. So now I have dx by itself, I have x by itself, and I can just plug these into this equation to get my x's out and thetas in. So I do that. Here's what used to be my x, and here's what used to be my dx. So now that I've gotten my x's out and thetas in, I just got to do all the algebra now. Let's simplify, follow the algebra, and see what we end up with. So I carry out the squared here, end up with a sine squared of theta and 4. I bring out my 1/2. My 4's will cancel here. I instantly recognize this as one of those trig identities. I know that this is just cosine squared of theta, so I'll write that. of course, the radical of cosine squared of theta is just cosine of theta, and then cosine of theta times another cosine of theta is just back to cosine squared of theta. So my algebra basically reduces me down to this integral. I don't know the antiderivative of cosine squared of theta off the top of my head. So I start thinking of my higher level integration techniques. I always think about u sub first. So I might try a u as cosine approach. Well, for that to work out, I need to see a sine of theta times a d theta. I'm not too worried about that negative one because I know I can move that to this side over here with no problem. But I do need to be able to see a sine of theta times a d theta in here for this u sub to work. Well, if I turn this cosine squared of theta into 1 minus sine squared of theta to make a sine up here, well, now I don't have any cosines. So now I don't have anything to make my u, and I don't even have a sine of theta getting multiplied by a d theta. I have sine squared of theta times a d theta, in a sense. Of course, if you're working it in your head, you might say, well, can't I try a u is equal to sine approach right here? Well, you could, but you'd run into a very similar problem that we do here. I mean, if you make your u sine, that means we need to see the derivative of that sine elsewhere in the equation, so we need to see a cosine. So we would flip this back to cosine using the trig identity, and we would just be going in circles. So u sub is not working here. I do know I can split this cosine squared using the half angle identity for cosine squared. So I'll do that. I'll end up here. Of course, this 1/2 can come outside the integral to make a 1/4. And now I'm looking at this integral, and now it doesn't look too bad. The antiderivative of the one part will just be a theta, and the antiderivative of cosine of 2 theta, well, that is a u substitution logic right there. You can do a u substitution, make that 2 theta your u, and you can make that work. But I won't show those u steps there. So antiderivative of 1 is just theta. Antiderivative of cosine of 2 theta is a sine of 2 theta over 2. And I got this guy by doing a u sub. And if you get a lot of practice with u sub, you'll get so good at it that you can basically do it in your head. So now I need to get my x's back in. Well, for this theta right here, that's no problem. If I look at my initial substitution, I know I can look at this sine of theta, and I can basically do sine inverse of all this stuff is equal to theta. So this is no problem. Getting that theta out of there and x is back in, no problem. This guy, though, that's a bit of a problem. I mean, what I'm seeing right here is sine of theta, not sine of 2 theta. So I wouldn't be able to put this in directly. But I know there's one identity that has sine of 2 theta exactly, and it's the double angle identity. So I put the double angle identity in here, and of course my 2's will cancel. Now to get my sine of theta out of here, no problem. Sine of theta is equal to 2x over 1. Not a problem there. But for my cosine of theta, I mean, if I look at my initial table substitution, I don't have cosine of theta. That's where this triangle comes in. This triangle helps at the end, the very end of your problem. That's where it comes into play. I know the cosine of any angle is the adjacent of that angle divided by the hypotenuse of it. So instead of writing cosine of theta, I can write the adjacent 1 minus 4x squared over the hypotenuse 1. And if I do that, I will get my final answer. So these trig sub problems aren't too hard at the beginning. You just look at your problem and see what table entry you would use. Use that table entry. Don't forget to draw the right triangle that your table entry describes by getting that trig function by itself. In this case, it was the sine. And from there, it's very much like a u sub. You want to get your x's out and your theta's in. So you get x by itself to put it in for x. Got to take the derivative and get dx by itself to plug it in for dx. And from that point, it's just a lot of algebra. And don't forget those trig identities. We use the half angle identity right here, and we use the double angle identity right here with the sine of 2 theta. So just always be looking for those. If you have those memorized, they'll really pop out to you when you see them. So next problem, a little bit faster this time. I see that Pythagorean theorem, sum/difference of squares situation going on. And I see this entry. My squared numbers are getting separated by addition. So my a squared maps to my 16. Take the square root. A is 4. My function of x squared piece maps to my x squared. Take the square root. My f, my function, is just equal to x. So I write out the substitution the table tells me to do. My f, which is my x, is equal to a, which is 4 times the tangent of theta. Of course, as soon as I do this, I'm going to write out that right triangle that this situation describes. So I get tangent by itself, and I knew that the tangent of an angle is just the opposite, which is x, so x is the opposite, over the adjacent, which is the 4 in this case. So here's my 4, here's my adjacent. So to figure out my hypotenuse to complete this right triangle, I do Pythagorean theorem, my 4 squared plus my x squared, and square root of all this, and that'll be my hypotenuse. So hypotenuse is going to be 16 plus x squared. Alright, my triangle is completed. So just remember to always do that. But now it's as easy as getting my x's out and theta's in. So x is already by itself here, so that's easy. I don't want to forget to take the derivative of it too, because I want to get this dx out. Well, derivative of this x equation here is 4 secant squared of theta. Of course, I multiply both sides by d theta to get the dx by itself. So now that I have x and dx, I can plug them into my main integration equation. Alright, so let's just crunch that algebra. I bring this 4 outside, there it is. I square this 4 tangent to end up with a 16 times the tangent squared of theta. I see a 16 and another 16, so let me just factor that 16 out to get here. Now I know this guy, that's one of those identities. That's just equal to secant squared of theta. Alright, so that's no problem. So I'll perform the radical of the 16 and then the radical of the secant squared of theta, and I'll get a 4 in the denominator and a secant of theta. This 4 can come outside. It'll cancel this 4. And I've secant squared of theta here. Well, that will cancel out the secant of theta in the denominator and just leave 1 secant in the numerator. I don't know the antiderivative of secant off the top of my head. I don't see a good u sub situation. An integration by parts approach doesn't look that good. I mean, I would have to make this my u and this my dv. So if you do that integration by parts real quick, the second integral you'll end up with is the v, which is going to be theta, and the du, which is going to be secant theta tangent theta. That doesn't look like a nice integral, so I'm going to conclude that integration by parts isn't the best choice. And trig integrals doesn't look good because I don't know of any identities with just secant of theta. So this is one of those integrals that a lot of people memorize. I myself have not memorized this. So you may just want to memorize that the antiderivative of secant is the natural log of the absolute value of secant of theta plus tangent of theta, of course, a plus c. Alright, so hopefully one day I'll remember that. The proof for it is actually pretty clever and non-intuitive. Like, I would never have been able to prove that myself. I mean, I know for the antiderivative of tangent of theta, d theta, I know you can split the tangent into a sine over a cosine and then use a u sub as cosine, and you can make that work. So I never have to memorize the antiderivative of tangent. I can always prove it, but the proof for this antiderivative of secant is just really hard from what I've seen, very non-intuitive. So maybe you just want to memorize this one. So antiderivative of secant of theta is a natural log of secant of theta plus tangent of theta. Okay, that's great. The antiderivative is complete. Let's just try to get our x's back in. So, secant of theta. Well, if I look at my table entry that I used, it involved tangent, not secant. So I know when this happens, I can use my little right triangle. That's the whole purpose of this thing. So remember, secant is the flip of cosine, which makes secant the hypotenuse over the adjacent. So that's all I have to write here. So natural log of, instead of secant of theta, I write what secant actually is, the hypotenuse, that big radical, over the adjacent, that 4. Alright, got it. Got a plus sign. And then the tangent of theta. Well, luckily, tangent of theta was part of my initial table entry substitution. So I know that tangent of theta is just x over 4. So that's all I have to write. So instead of tangent of theta, I just write x over 4. And there is my answer. Alright, so not too incredibly bad. Looked at our Pythagorean theorem situation. It's the second table entry. So we rolled with that. Crafted that second table entry. Remembered to make that right triangle. And then it was all about just getting the x's out and thetas in. That got us here. And from there it was just following through with that algebra until we got here. And then we had that weird antiderivative of secant going on. Alright, so let's do one more problem here. So I see my Pythagorean theorem situation. Now notice that this is not a perfect square. It's not like a 16 whose square is 4. It's not like it's 64 whose square is 8. This is a 7. Well, the square of 7 is just, radical 7. It doesn't come out perfectly. So, a little bit of imperfection here, but we can still use Trig Sub on this. So I'm going to use this last identity right here because we have our thing with x in it squared first, then the minus, then the number squared. So my f squared is my x squared, which makes my f just x. My a squared is my 7, which makes my a just the radical of 7, whatever number that is. Probably a 2.5, maybe, who knows. Alright, so let's craft our substitution. We'll But that's as easy as x is equal to root 7 times the secant of theta. Of course, don't forget, let's make that right triangle. That'll save us at the last step. And to do that, I want to get the secant of theta, that trig part of it, by itself. And I know the secant of some angle is its hypotenuse side over its adjacent side. It's the reciprocal, it's the flip of cosine. So let's draw that right triangle. Of course, I want my opposite right here. So if I do my Pythagorean theorem, that'll be x squared minus root 7 squared. And of course, radical 7 squared is just going to be 7. So my triangle is completed. So of course I need to take the derivative of this guy to get my dx symbol to appear. So I can get the dx out of there and theta's in. So not too bad of a derivative. Just got to remember that the derivative of secant is secant times tangent. And of course we'll multiply both sides of this equation by d theta, so we can get dx by itself. Alright, so I got x, I got dx. Let's just throw them into this equation here. Alright, so I threw it all in there. And of course, we want to clean this up, simplify as best we can. So I know a radical 7 here times a radical 7 here will just make a 7, which I'll move to the outside of the integral. I'll do that. I also took these secants, multiplied them by each other to make a secant squared of theta. And I carried out this squaring right here, so I ended up with 7 times secant squared. Now I know I can factor out my 7 here. And this guy just is an identity. I'm always looking out for those identities. I've just memorized them so much that they just pop out when they appear. So I know this is just tangent squared of theta. And of course, algebra allows me to take the radical of the 7 and multiply it by the radical of the tangent squared. So if I do that, I'll get just radical 7 times tangent. I get a tangent cancel here. This radical 7 is a constant. I can get them out. So it looks like all this mess cleans up to this. And this integral makes me really happy, because I know the antiderivative of secant squared is just tangent. I know the derivative of tangent is secant squared. It's just something I memorize. So therefore, the antiderivative of secant squared of theta is a tangent theta. So with this antiderivative done, it's pretty much smooth sailing from here. Of course, I can't leave my final answer with theta in it when the question was posed in terms of x. Gotta get our x back in our equation somehow. Our trig substitution table entry had secant. This is a tangent, so I know I gotta use my triangle here to help me out. We'll never forget, tangent of an angle is the opposite over the adjacent of that angle. So I just took that tangent and turned it into opposite over adjacent. And there we go, that's that. So this problem wasn't too bad. It was a little bit weird with that 7. 7 is not like a perfect square, not like 49 or 84, 64. So just because you don't see a perfect square here doesn't mean you can't use the Trig Sub technique. So hopefully this video got you some good practice in solving these Trig Sub problems. I like Trig Sub. I think it's a lot less stressful than some of the other integration techniques like U sub or integration by parts, where you have to choose a U and you have to choose a U and a dv. You really have to think hard, alright, which choice is the right choice, or is this choice bad, or is it going to lead me onto this really bad path and end up at a dead end with some really gross algebra. Nope. Just, if you see that Pythagorean theorem situation going on, just make that correct table choice. Don't forget to draw the right triangle, and then get all the x's out, theta's in, and just roll with the algebra. And don't forget those trig IDs, because many times they'll help you out in this trig sub technique as well.